Okay, let's give it 1 more minute for some more people. I guess some more are joining last minute. So I want to thank you for making it to the second rescheduled webinar in such a short notice. As I said before, we had a technical issue. On this webinar, which is part 3, we will be covering different aspects. So we had two webinars in the past weeks on the design of deep excavations, looking at specific examples. So we're going to be looking at how we can optimize excavations. We're going to be looking at the cantilever excavation, 10 feet to roughly 3.5 meters. How to optimize an excavation with 1 tieback level. Look into a nonlinear analysis with 1 tieback level. We're also going to look at that excavation that we did 50 foot deep, roughly 15 meters with the 3 levels of tiebacks on the previous webinars. And we're also going to look into a 10-meter cofferdam, so we have to have a balance between English and metric units, with 2 levels of struts, and how that can be optimized. All of this is going to be done with the software program that we have developed, tiebacks. So if you need to refer to the previous webinars regarding the theory, please let me know, and we'll be more than happy to share those videos with you if you haven't seen them. So we're starting the program, and we're going to go step by step. So first of all, the program is interactive. If you have any question at any point, please use the chat and write your question. So you can double click on the walls, see the wall section that you have. You can change the elevations of the water table or the surface. But you can also drag the surfaces, so you can press the mouse and excavate like that. We can add the stage, add the second wall, excavate, draw. So I select draw a ground anchor here. So we can click on the first wall in the ground. That installs the tieback. We can draw loads as construction loads, loads on the wall. You can put prescribed line loads, moments, and so on. We can add a 3-dimensional footing, or we can even add a building. So we have a nice building behind the excavation. And we can always go view, top view, and we have 3-dimensional loads. We can see where that building falls in relation to our design section. So this quickly tells you what you can do. You can go and press delete, erase the building, right-click, deactivate the tieback, activate. In terms of the supports, you can draw in a strut from one wall to another. You can draw in a raker. And you can do quite many things. So right now, we'll go on top, press delete. Just so we start from the very first, from the beginning. So let's delete the second wall, delete this footing. And while we can build the cantilever excavation quite easily this way, let's actually use the wizard which guides us step by step. So we'll click on the model wizard. We'll use English units. Metric are available, of course. We'll run a limited cantilever analysis. And we're going to select to optimize the wall embedment. We're going to be looking for a 1.5 safety factor because it's a cantilever wall with the free earth method. So we're going to see that we're going to have a 10-foot excavation, and we're going to start off with a 15-foot wall length. We'll say that the excavation width is 50, let's say 60 feet, and our ground top elevation 0, our groundwater elevation at elevation -15. Now we don't need to worry too much about the rest at this time, but these are some of the wall types that we can build with the wizard. We're gonna put our soil types, and what we'll do is we have our first soil name, color, the soil type, we're gonna use sand. We're gonna put in our unit weight, let's say below the water table, 120. That's roughly 19 kilonewtons per cubic meter. A friction angle of 30, let's say a friction angle of 30. We're going to skip the rest, and we're also going to use the soil type S1, which is another, let's say, sand. We're going to define 125 pounds per cubic foot for the unit weight. And we're going to use 100 psi cohesion and 36 degrees friction angle. Now, there's also ways of estimating properties from SPT test data. There's recommendations here, anywhere that you see something like this. So we could, in fact, estimate the friction angle and other parameters from SPT. There's also a tool to drag the SPT values along like that and get a rough estimate. I don't really like using tools like that. I'd rather have tests, but if you have to, you can use it. So we can click OK. We can click Edit Borings. And we'll put in elevation minus 15, and we'll use this S1 soil type. We can add new borings that can be used in different design sections where we can use different soil profiles, but we'll use this boring one right now. On the wall type, we'll click Edit Section Data. We can see that we have soldier pile walls, reinforced concrete, steel beams, steel pipes, and unreinforced for soil mix if we want it. Sheet pile walls, secant piles, tangent pile systems, diaphragm walls or slurry walls as in the United States, soldier pile and tremendous concrete, and we also have combined king pile and sheet pile walls. So let's actually select the sheet pile wall here. Then we'll go to stages. We'll say cantilever excavation. We'll use a strip load, 0.6 KSF, 20 feet behind, wide, 2 feet behind the excavation. And here we can select the structural codes that we want to apply. We'll select US allowable stress design. We won't build any load combinations or Eurocodes at this time, and we can select OK. So this is our model, 2 stages, stage 0, no excavation, stage 1. I'm going to right click, add the next stage here, no excavation. And the only thing I'm going to do is I'm going to go on stage 1 and deactivate the surcharge. And the reason I'm doing that is because I want to see the impact that the surcharge has. So we can run this analysis from here. And basically the program has come back with a summary of the analysis. So if we look at here, it says calculation successful. We get our wall displacement estimate, surface settlement, wall moments, shears, structural checks on the wall. So the structural checks have to be smaller than 1. They're like stress checks. And we also have stress checks if we had supports. And our wall embedment safety factor, so the program automatically determined 1.537. It changed the wall length. We can also see the results for every stage here. But the nice thing is that we can view those results directly on the screen. So we can see what the wall moment is, the pressures, lateral pressures on the soil, the surcharges, the net horizontal pressure diagram, the shears. Now, when we see, when we're looking at here at the moment envelope, this is the moment on this stage 2. This red line is the design capacity of the wall. So one of the things that we see is that we're actually, well, we have optimized the length, because if we click on wall embedment safety factor, our wall embedment safety factor is 1.537. We're not really so much optimized for the bending moment. So this looks like it's over-conservative. So we'll go to optimize. We can select optimize the wall, auto design a wall. Select this wall here. And the program recommends the 10 most effective seed pile sections. And you can use any one of those depending on what you want to use, and depending on also on what you have available. So let's select this section, or we could go with an AZ12. And once we're done optimizing, we know what the wall length is, so we don't have to change that. I went to the design tab. I've taken out the optimization for the wall embedment. We run the analysis, and we're seeing that the stress checks are more reasonable and much closer to the bending moment. So this, in essence, is our first simple optimization case. Now, what we'll do is we'll build up on this, and we'll actually add the tieback. So we'll add the stage after the cantilever. We'll go to the General tab, Draw Supports, and we're going to draw a tieback. Select Enter first tieback point on the wall. That's what it says here. Go on the wall, click on the ground. We're going to put it at 8 feet depth, or elevation 80, minus 8, sorry. We're going to put a 20-degree inclination angle, and we're going to start with a free length, let's say, of 15 feet, which I know it will not work. And let's put a spacing of 7 feet here. Next, we can put a pre-stress, let's say 55 kips. We're guessing something, but we'll find that number out. So, and the reason I'm putting a pre-stress is because we're also going to do a nonlinear analysis. Now we're seeing that the tieback falls here, so that our model is not sized ideally. So what we'll do is I'll click on the model dimension limits here, and I'll change the left coordinate of the model to -60. So this looks like a better sized model. We can right-click, add stage, and I'm going to drag the excavation, the right, to elevation -21. Now on the yellow table, we see that the water assumptions, we're assuming hydrostatic in our analysis. Apparently this is not sufficient, and we're also assuming active earth pressures Ka. So if we go in our analysis, this is where we control our analysis type. This is where we can generate all LRFD and Eurocode combinations. This is how we control how the clays are. So let's actually do what we wanted before. We'll change the pressures from the water pressures from hydrostatic to simplified flow. We'll do it for all stages. And we will use FHWA apparent earth pressures. Now, if we have to optimize this, typically a safety factor of 1.3 is used. So we'll go on our design and we'll say optimize this, but please use 1.3. So we'll restart the analysis. So the program is iterating right now. So we've come back with our displacement. And there's some right here, so maybe we've missed something. Calculation successful, however, items might be unsafe. So let's actually find out what's missing. So when we got the models are working fine, we have the critical support check. So this means that our supports are overstressed, and we're seeing that the geotechnical capacity ratio pull out, the ratio is 3, which means that we have a 300, our force is 300% greater than what the design value is, actually 200% greater, we should say. And we can actually see the warnings. So we have these warnings here regarding the support capacity. And we can see those results for all the stages. So what we'll do is we'll exit. Now the reason that we're getting this result is because if I double click on the boring and go on this soil type S1, we haven't specified sufficiently, we haven't looked really too much on this ultimate borne resistance for the tiebacks. Now this can be estimated from pressure meter tests or FHWA recommendations. So let's say that we had, I'll say 40 psi. I know it is not the most conservative. On the other soil type F. So now we'll rerun the analysis, but we don't have to optimize the wall length again. And we're here. We're still overstressed, so we probably have to optimize the wall, the tieback length. So let's go optimize. And what we're going to do is we're going to say optimize design section. So this is going to try and optimize both the wall and the tieback. So we'll wait a little bit. Here's our option for the sheet pile walls. We have the 10 most effective steel sheet pile sections. I'll maintain the AZ12. And we fix the length, we change the length of the tieback from 15 feet to 25 feet. So that's an optimized design. Maybe it's not the most conservative, it's actually, maybe it's conservative, but this is an optimized design. We'll reanalyze this, and let's actually view the earth pressure diagrams. So we'll click on the earth pressure diagrams, and these are right now our apparent earth pressure diagrams, our passive pressures. We can see the vertical effective stresses, the water pressures, and the net water pressure coming back to zero because we're doing a simplified one-dimensional flow analysis. So with that, we can actually add, right-click, and I will add a new linked section. So this new linked section, actually, let's click on the first one and say conventional analysis. And we'll go in the new linked section, right-click, edit name, and say nonlinear. So we're going to run nonlinear analysis. And now we're getting roughly 12 kips per linear foot. And if we click and go results, that's 83 kips on that tieback. So when we go on stage 2, the first stage 3, where we're activating the tieback, we're putting 55 kips. That's roughly 70–60%. So let's say something like 60 here to adjust the pre-stress. But we have to make sure that we edit the nonlinear properties of this of the soils. So go to General, Elastoplastic. So here's where we have the elastoplastic soil models. We have a linear elastic perfectly plastic, an exponential, and a subgrade reaction modulus. I usually prefer the exponential. So the idea is that we will need some SPT value to estimate the loading modulus of elasticity. We have the exponents for loose sand, and coefficients for vertical and horizontal stress, and the reloading modulus for the excavation side. So let's say we want to estimate from SPT. We can color type, soil type that describes better our situation. We can go in with an SPT of 10. It comes back with 532. I will probably round this up to 500. We never know the modulus of elasticity that well. We can go on soil type S1. Let's say that this is a stiffer soil. So we can say we have, for example, 20 blow counts. I will round this C loading to 650. So with that, we can run the nonlinear analysis. The way it is controlled, the model here between these two design sections are linked, but not the analysis type. So we can actually go here in the analysis and change this analysis again to the equilibrium if we wanted, but it won't make sense. So the idea is to have a separate design section with a different analysis mode. So let's run everything. So we're coming back with our estimates of wall moments, shears for the two different analysis types, and wall embedment safety factors. So we're getting around 1.394 on the nonlinear analysis, 1.4 from limit equilibrium. The difference is that the nonlinear analysis automatically balances out all the moments towards the bottom of the wall, the shear, but it also, we're also building up our displacements based on the previous states, on the pre-stress of the tieback. So we got here the cantilever displacements with the surges behind. We're putting the tieback pre-stress, the wall is moving back, we're excavating further, and this is how we complete our analysis. Now let's say that we wanted to perhaps reduce theoretically and justify smaller reactions. Maybe this is too big for our experience, and we say, look, I expect something else. So what we can use as a trick is actually we can apply in the analysis, we can go and apply wall friction. And I will start small with the wall friction. I will say 33% of the available soil friction. And in the design, we can re-optimize the length for 1.3. Rerun the analysis for both design sections. And we can see what displacements we get and what wall length. Now the wall length reduces. An important thing to check on our wall embedment safety factors is that our hydraulic heave safety factor stays above 1.5. That's a general recommendation. But now what happens is that our support reactions have gone down, our wall displacements have gone down since we've assumed wall friction, and our required wall embedment has also gone down to 7 feet. Now, my general feeling is still that I would specify at least 10 foot of wall embedment because sometimes there can be over excavations and so on. But theoretically, at 7 feet, you will be fine. You will need more. But it's nice to be a little bit extra safe with wall embedment. If you over excavate, you don't have any other means of holding that wall there. So I want to see if there were any questions so far on this part. Okay, I don't have any questions yet. So what we'll do is we'll export this, we'll go to report, report options, select all the stages, and we can preview the report format here, export to PDF and export to Word. So we're going to preview this. And this is what the report looks like. It gives you a summary of the moments, the structural material data, each of your design sections, moment envelopes, shear envelopes, displacements. And we see the excavation stages, soil pressures, water pressures, displacements, moments, and so on for all the models. So you can include a lot of data. There's also the possibility to include the equations for the supports or the wall. So if I did this, let's see, erase, and I said critical wall equations, preview, the program actually reports to you all the stress checks and structural calculations done for the walls, the supports, and so on. Now I've deliberately just put this so I've kept it short. So now that we've done this, which is quite simple, we'll go and use the wizard to do that 50-foot deep excavation that we studied with the verification examples on the previous 2 webinars, and we did all these nice Eurocode things and the LRFD. So We're going to run, first of all, limit equilibrium analysis. We're going to optimize targeting 1.3, safety factor, per Caltrans. We're going to use California trenching manual. We're going to make a 50-foot excavation. We're going to start off with a 65-foot wall. Let's actually do a 70-foot wall, that's fine, because we know what the answer is when we get close. So we're going to put the groundwater at elevation minus 35. We're going to do tiebacks. The tiebacks at 15 degrees. We're going to space them at 5 feet horizontally. We're going to edit our borings, soil types, let's remain the same for the time being. So we're going to assign boring 2. So you see that I haven't really destroyed boring 1 here. We're going to keep the same wall type, but change it further down. And on the elevations, I'm going to enter the depths, 8, 22, and 36. We're going to put a strip load, 0.6 KSF, 20 feet behind the wall, 20 feet wide, 2 feet behind the wall. And we're going to keep US allowable stress settings. So the program created all the excavation stages. Now we're using still hydrostatic pressures here. I'll go in the analysis and we'll use a simplified flow. And we can actually run the analysis right now the way it is. So the program is optimizing the wall embedment length. On the yellow table, we're seeing the assumptions that we're using California soil and trenching manual recommendations. We're seeing what we're using the simplified flow, FHWA pressures, and we're using wall friction. So we see that we're getting red here. And in fact, we're exceeding the wall bending capacity. We're exceeding some of the geotechnical capacities of the tiebacks. And also we run the nonlinear analysis, and here we're exceeding the design capacity of the wall. Now we didn't change, we just have an AZ12. The program optimized the wall embedment length to 17.6. So we want to, let's actually do something here. We'll say optimize design section. So now the program looks at the wall section, the tiebacks, and recommends that we use an AZ24 for a seat pile, and it optimized the tieback lengths and the number of strands. Now we'll rerun our analysis, but we'll just make sure that on the design tab we don't need to optimize the wall embedment length right now. And we're seeing that we just have a small overstress right now on the wall, 2.9%. You might call this acceptable and say that's fine. Or another option here is really when we go in our conventional analysis, we have to actually control the pre-stress. So we might actually want to apply a greater pre-stress on our wall. So when we go here, we might say, I want a greater pre-stress here. So I'm going to double click on this tieback, and I'm going to apply 85 kips of pre-stress. So we're pulling our wall a little bit further back. These are some of the things that you have to play around, especially when you're doing the nonlinear analysis. The limit equilibrium analysis will give you just a single number. So now everything looks much closer. So this will be an almost 100% optimized design in terms of tiebacks, lengths, and so on. So let's reanalyze it here, make sure that everything is running fine. Now you might, if you want to decrease some of the displacements, you might actually want to increase your wall length. There's a number of things that you can do. Increase your stiffness, increase the pre-stress. And one of the things that somebody will see is like the displacements here building up from stage to stage. So your pre-stress is making a difference. Your wall stiffness makes a difference, and so on. On the other hand, on the conventional analysis, you're just seeing the last stage, whereas in fact, your previous stages, how they're building up, the displacements, are not really accounted for. So we're totally ignoring all this interaction, and we're just assuming a very simple behavior, especially with the Caltrans approach. Now, remember that we looked at different design up methods for limit equilibrium analysis, and typically what I'll do is this. I won't create different models, but I'll say I'll run this with Caltrans, but I want to see what my other design methods do. So I'll add another stage, edit name, I'll call this FHWA. So I'll go in the analysis tab and select FHWA simple span, but not for all stages. I'll add another stage, and here I'll use simple span with negative moments. No. So edit name, simple span, negative moments. Actually, I guess I did not edit the name. Simple, negative moment. And we're going to add another stage, right click, and I'm going to use Caltrans here, but with more options. So I'm just going to put a 20% negative moment just on this stage. And then there's additional options for Caltrans, and I'm just going to apply them to the current stage. So if we run this design, what in fact we can see is, like on the final stage at least, we can get a sense of how the bending moments, support reactions change from method to method. So you could actually create different design sections to look into that, but in the limit equilibrium analysis, you can actually specify all this. So you can see the bending moments. So if we went Caltrans 65.6, FHW 33.7, simple span moment 51, and the Caltrans with negative moments 57.6. And you can also compare the reactions on the supports as well, and the stress checks, and your wall embedment safety factors. Now, do you have any questions on this part? Okay, so it seems that we're doing well here. I don't see any questions. Okay, so let's actually move on the next part. We're going to do a strut excavation, so I'm going to start from new. We're going to use our wizard, and we're going to do metric units. We're going to run both analysis. Actually, let's run a limit equilibrium analysis here. FHWA, Caltrans. We can actually run a nonlinear. Let's do a nonlinear analysis. It might make more sense. So next, so we're going to start with a 10-foot excavation, 10-meter excavation, a wall length of 15, an excavation width of 12, and we're going to do a full cofferdam here, the groundwater at -10, and one wall length 12 meters, let's say the other one 22. And we're going to space our tieback, our struts at 5 meters. We're not going to edit the soil layers at this time, but we're just going to say edit borings. So we're going to go at -10 elevation and apply a clay. In clays in our nonlinear modeling, it is important to specify the overconsolidation ratio because that controls your undrained shear strength. We're going to click Edit Section Data. And here we're going to select the secant pile wall. So we're going to put the piles inside the 0.6 meter, the beams inside the 0.6 meter pile, spaced at 1 meter. We can control the steel that we want. We can control the beam. And this is what our wall looks like. We're going to go next. We're going to put automatic elevation, so we're going to equal space 2 numbers of supports, so 2 strut levels. We're going to go next. We're going to put a strip load, 15 kPa, 6 meter wide, 1 meter behind the wall. And we're going to analyze all British Eurocode cases. Select OK. So the program is recommending that we change the structural settings. We say yes. And what the program has done is that it has first of all built up all our stages. Then it has built up a design section for design approach combination 1. Now think of it like a load combination for LRFD, and another for design approach 2, combination 2, design approach 1, combination 2. And the program also created it assumed some sort of a design for our cofferdam. We're going to forget this for the time being and just analyze the excavation. So we have our summary of results here. Bending moments on the walls. We can show the envelopes. And we can show the global envelope where we can see from all the design sections with the British Eurocodes or LRFD if we were to do them. So we can see those envelopes. We can see the pressures and the wall displacements. And we can go on the project plan and optimize. Well, what we'll do is, like, I don't like, let's say, exactly how this is laid out. So if we go in 3D, we can actually double click on the struts and control exactly how they're located. So there's a wizard there. It does something. It proposes a layout, but it might not be, say, ideal. So just double click. And in fact, you can actually draw in struts like this. I'm deleting it right now, or draw tiebacks. Ideally, you don't want to mix the two. So now we'll have the first strut level at elevation -3. We'll have to go and change the second strut level. So we'll run this analysis here. With the 3D frames. And we're seeing, first of all, that our whalers are overstressed. See how they're in red? These are the results for the whalers. The struts look fine. We can see the bending moments on the whalers and their stress checks. So we can see where we have overstress and also the stress checks on the whalers. So if we want to optimize this, this can be done actually quite quickly, or relatively quickly, I would say. So we can press optimize all. I'll select that. And now we're waiting. The program is looking at the roughly 300 different steel sections, trying to optimize all our whalers and all our struts. So back in the old days, you will have to do this by guess. Now this can be done almost automatically, but you still have to make sure that you select an optimum design, an optimum layout for your struts. Now the layout for the cofferdam doesn't have to be rectangular. You can pretty much do whatever shape you want. The way it works is that it picks up the loads from the 2D analysis, and it assumes the worst load scenario that you have used in each design section or each wall section. You can actually, even further if you want, you can actually specify concentrated loads specifically, where you might have a building and simulate that you have a higher load there. So let's wait and see the numbers that we get. Do we have any questions, please? Okay, I don't hear any questions. Now the program is still computing here. Sometimes I'm thinking about whether I should be doing this optimization directly on this webinar because it's taking 1 or 2 minutes. But the idea is that the program will do this much faster in terms of what is required. Now there's different options where you can explode all the items here. So you can explode all the whalers individually. So you're using different whalers and different struts at its location. And that way you can optimize every single whaler. So there we go. So we got the first recommendation, W33 by 130. I might go for the W24 by 131 because it gives me a slightly better stress check. We've optimized our whaler to a W24 by 131, and now we're optimizing our struts. These are in millimeters. So we're doing a W, let's say we're going to do a W36, actually 366 millimeter pipe by 10 millimeters. So we'll have optimized our excavation. We'll run the analysis to make sure that everything looks fine. And everything looks fine this time, so we'll have a nice design. The program also gives you an estimate for the walls, the struts, the tonnage for the steel, supports, whalers, excavation volumes, and so on. So this is something that can help you actually, if you want, it can help you and you can use that to prepare an estimate. At least you can make the quantities very quickly. So this covers pretty much the basic capabilities of the software. Let's actually do some other things. So I'm gonna add an empty section here. And what we'll do is I'll lower the excavation on both wall sides, on all sides. So this is our initial condition. We're putting our walls here. Apparently we'll be putting secant pile walls in a case like that. Let's actually put a sheet pile wall, or we can actually put a soldier pile and lagging, but let's actually put a sheet pile wall here. So that's our sheet pile wall here. And we can change the sections if we want, or the location of where that wall is. And what we can do is we can draw in, we can add a stage, general, and we can draw a tie rod or a ground anchor really from one wall to the other, change the spacing. change the section, so I'm going to put a new solid bar, let's say grade 75, simple bar. We can put the number 18. We can also import from databases. I'm going to add another stage, and we're going to backfill. We're going to add another stage. We're going to draw a load. We are going to add another stage and excavate on one side, and also excavate on the other. So I don't know how this is going to work actually, but I'm curious, let's actually see this. So it says analysis did not convert, but it was nice to try out. There was probably too much load in one stage. Let's actually try and change that spacing for, I'm using struts. So let's actually put that solid bar. I know what's happening here. The thickness of the strands actually is not as great, so when you're doing something like that, that's why everybody's using solid bars. There we go. So let's actually clear up the screen a little bit and see what we get. So let's take out the dimensions. So the interesting thing is to watch out, and let's take out the stress checks. So we have stage 0, we're putting in the tie rod. And we're seeing what the displacements are. We can take out the wall moments, and we're seeing because we're excavating more on this wall, the two walls are connected with the tie rod, so we're actually pulling this wall a little bit further back compared to this wall. So we see that we have the interaction between the two systems. Now, another interesting thing that we can actually do, so if you have completed your excavation, we can actually add a stage. We can actually start building up our base slab. So we can change this slab here. I'm going to make it pin connected. I'm going to assume an embrace length here, let's say 3 meters, just to make sure that it's supported. We can control exactly where that slab is located. I'm going to put it on the center. So that's our first slab. And we can deactivate that strut, so we can start building up our excavation. We can add another stage, and in fact, let's actually add the structural wall section here. So we'll add the basement wall, and I'm going to use a diaphragm wall, which is a concrete wall. So we have the reinforcement here, but you can change that if you want. And let's say here, I'll make sure that it's, let's say, basement. So we want to build our permanent wall, and what we can do is this. We can draw in our basement wall from here to here, change to basement, let's say -3 meters to -10, position on the right side of the main wall. There's some advanced features that we're going to say element behaves as slave. So we have connected this slab here, and we can also, this basement wall, we can also connect the other basement wall on the right side. Also connected on the slave nodes. So we have the main wall, and also we can do another slab. pin connections. And we can also connect it to the slave nodes. So there's a couple of more tricks that you have to do here, but the idea is that once you do that, you can remove that strut and you can model the whole construction sequence with the slabs. And there's also possibilities in the analysis that you allow tension gaps to form between. So I went in the advanced analysis options. So we put tension gaps between the basement wall and the temporary wall. So with that, I'd like to see if there are any questions, please. You can also do circular excavations if you'd like. Any questions, please? Either it's too late in the day. Yes, Bakri, please. Okay, Bakri, let me know. What's your question? I don't hear any questions so far. Okay, say, is it possible to calculate the pressures when there is a slope over the piles? Yes. And there's a question by Christian Radu. Can you model earthquakes? Yes, you can model earthquakes, and it's also possible to calculate pressures when there is a slope over the piles. So in fact, let's actually do this. You can backfill and create an arbitrary excavation like this, a surface like that. We can even go in the analysis and use custom layers, reset the layers from boring, and you can actually draw in. You don't have to have a horizontal ground layer. So you can create something complex like that. And in this case, there are two options in the analysis. One is that you can analyze with Kalman's method with active wedges, or the program can also do a slope stability type of search to find the active and passive earth pressures. In the analysis for the seismic, we can include seismic loads. There's advanced options here for the method and so on. But the idea is that we can define our acceleration, let's say 0.1, and on the method you can say what type of pressures you have, Monobel, Cabe, and so on. And on the water behavior, you can say if it's pervious, impervious, so you can add hydrodynamic effects as well. One of the things I didn't cover, you can also do a global stability analysis. So you can select to perform a global stability analysis and do that as well. So Christian, it's not a bad question. Any other questions, please? Okay. So I want to thank everybody for attending this webinar and seeing what we have to offer here. Feel free to contact me if you have any questions. Now, we haven't really covered all the aspects. You should have my email address, dimitrios@excavation.com. Also, if you happen to be going to San Antonio next week for the IFC conference, I'll be more than glad to see you there. There's a number of interesting things happening, and I want to thank everybody for attending this webinar. Feel free to ask questions. Thanks to everybody. Okay, see you hopefully soon. Thank you. Bye-bye. There's a question by Christian Radu. If we're using European design approaches, Christian, the program actually, if we look at seismic, in the analysis combinations, you can actually select which approach to use, and you can even use Eurocode 8. So there's combinations. You can actually classify your own. So depending on your design approach, if it has it, you can also use Eurocode 8. The other option, of course, is you can go inside on multiple combinations. You can import a combination, let's say standard combination. So you can select something like Eurocode 7. And then you can change the seismic multiplier. I don't remember exactly where it is. There it is. So if you put 1 on the seismic multiplier, that will cover you. Thank you very much, Bahri. Good night to you. Thank you, Zhao. Thank you, Patricia, as well. So the design approach, Christian, depends really on the country you are and what is being specified. So I'll stop the recording right now. I want to thank everybody for participating.